Hello everyone. So in this video, I'm going to show you how to use Python. And you can code Python inside a coding environment called Jupyter Notebook to obtain the solutions of a system of linear equations through the Gauss-Jordan elimination method. For those of you who are new to coding languages, so don't worry about that. I will walk you through a certain basic process that you can do with Python. And the need is not going to give you the full extensions or the full knowledge of how to code a Python, but just certain skills so that you can properly use Python to obtain the solutions of some system that you want to solve. Okay, so hopefully at this point you have installed Anaconda on your computer, and when you click on the Anaconda icon, this is what showed up after you click on it. So you have multiple options here that you can use. So most of the time, we're just going to use Jupyter Notebook, and you can hit launch and it will give you to another browser. I'm using Chrome on my computer, so it will lead me to Chrome. If you use other web browser, it will lead you to that particular browser. Another system or another environment that you can use is Spider. You can also use Jupyter Lab, but most of the time I just need to use a Jupyter Notebook. So now this is where it get me to, usually it give you, let me to here, this particular site. And in here, I have multiple folders on my computer. So I store the coding folder in desktop, click on that, and I go to code. And I have multiple language here. I want to use, sometimes I use MATLAB, sometimes I use Python. So I click on Python in this case. And to create a new file, Python file or Jupyter Notebook file, I'm going to go here, click on new, and hit on Python 3. Okay, so this is the environment that you're going to see. All right. So the first thing that I want to do is to introduce to use the NumPy library or extensions, and that will help you to deal with some mathematical objects, like create an array for means that can create a column vectors, row vectors. It's going to create matrices, which is very helpful for us because you want to create an augmented matrix in your code. So like I say, for this tutorial, it just show you some basics that allow you to deal with the mathematical solutions of system of linear equations. Not going to give you a full basic or the full knowledge of Python at all. Okay, but bear with me here. So the first thing that I'm going to enter here is I want to import the NumPy library into my coding environment. So what I do is I do from NumPy. I'm going to import everything. So the start here means that I'm going to import everything. So this syntax or notations is shift 3. This will allow you to comment the something that you want to say to the reader. Okay, so I want to say that NumPy in this case going to be the numerical Python extensions or Python library. Okay. For some of you who use Python before, there's another way to import NumPy. This is a more common way that people use. So import NumPy as NP. So if you import NumPy using this particular method, it's a little bit tricky because when you do this, anytime you have a syntax that you want to play with, or if you want to enter with, you have to start with npy dot that particular syntax. Okay, so if you want to play around with sine or cosine on an array, you have to do npy dot cosine or npy dot sine or npy dot array or anything related to numpy, right? So to avoid keeping typing npy dot, I'm just going to use from npy import start. I mean, you import everything in and you should be good. All right, so let me start by first create an array. Again, an array is another way to say that you want a matrix. Okay, so I'm gonna start with some vector, right? So again, we haven't formally defined vector, but it's just a bunch of number written inside a bracket, very similar to the case of matrices, right? So I start with X and I want to create an array. And the way to do that is you open and close parentheses. And then inside this parentheses, you have bracket. And I have the entries of 1, 2, 3. So for this particular array or vector, you have one row, only one row, and 3 columns. Okay. And I want to see this particular array or vector on the screen. What I do is I can print X, right? So let me explain this. So I want to print out the value of X, right? To run the code, it's very simple. You just hit Shift Enter or Shift Return. That will give you the array of 1, 2, and 3. All right. You can manipulate this particular array. You can do multiplication. You can do by a constant number. You can do divisions by a constant number. You can add of all the arrays of the same size, so on and so forth. We will get to that when we get to vector and matrices later on. But for now, let's just deal with arrays, right? Let's try to learn how to form a matrix. Another way to, for the print command, you can actually print our text, right? So for this, I do introductions to linear algebra, and you hit Shift Enter again, it will give you the text introductions to linear algebra. Not only that, you can create a vector, you can create, of course, a matrix. So in this case, I'm going to create this following matrix. Again, I want to use array, open parenthesis, and then bracket. Now, this is the matrix, right? So everything happened inside this particular bracket, right? So for matrices, you have multiple rows and multiple columns, right? So columns can be separated using a comma, and multiple rows can be separated by also comma, but for each row, you're going to use a bracket, right? So this is the bracket for the first row. Right, so this is the bracket for the first row, this is the bracket for the second row. So you have 2 rows. If you want another row, you use comma and then another bracket, and that is how you get the next row. Okay, so for now, let's just start with 2 rows. So in the first row, I have 1, 2, 3, and in the second row, I have 4, 5, and 6, right? And let me, so I forgot to close the bracket here. Okay, so now I want to print out this particular array or matrix. So I print capital A, then hit enter, shift enter, and then that gives me the array, right? So this is the matrix of 2 rows and 3 columns. So this is 2 rows, 1 row, 2 rows, and 3 columns. So 1 column, 2, 3 columns, right? So So here I want to comment that create a 2-row by 3-column matrix. Okay. So let's create a more complicated matrix. So I want to create a matrix B. Let me say that I want to create a 4 rows by 6-column matrix. Right, so I call this matrix capital B, and I have an array, open parentheses, close parentheses, open bracket, close bracket. This is where the whole matrix is going to happen. So the first row is going to be including the entry of 1, -3, 0, -1, 0, -2. Now that's for the first row. The second row is 0, 1, 0, 0, -4, 1. The third row, including the entries of 0, 0, 0, a bunch of 0. All right. And the last row, I forgot the bracket again. So the last row I get 0, 0, 0, 1, 9, 4, and I hit Shift Enter. So let me see. This is where. So I have some problem with the bracket. So this is the first row. This is the second row. I forgot to have an open bracket right here. So I'm still have some issues. So I have, I forgot to close the bracket again. Okay, so now that should be working. So Shift Enter again. Okay, so now you need to print out matrix B. Okay, so that's the matrix that you want to have. So we want to do with Gauss-Jordan eliminations, right? So it's include forming the augmented matrix and perform the elementary row operations, right? So there are again 3 elementary row operations. You swap 2 rows. You can multiply 1 row by a constant multiple, and you can add the constant multiple of 1 row to another row. All right, so to swap 2 rows, so I'm going to perform on B. So to swap 2 rows, I'm going to swap row 3 and row 4. Okay, but the weird thing about the Python is that how they index the number of row and number of columns. So they start with 0, and then 1, 2, and 3. Right, so that's how they index. But for us, we usually start by row 1, row 2, row 3, and row 4. So that's why I'm saying that I want to swap row 3 and row 4. But in Python, to accomplish that, the row 3 is now actually row 2 in Python, and row 4 is actually row 3 in Python. Okay, so to do the swap, right, so I have row 2, comma row 3 in Python. That means row 3 and row 4 by our counting. It's going to be equal to row 3, comma 2 in Python. So you swap the 2 rows. And I'm gonna print out B one more time, and this give me. So as you can see, the difference between this output and this output, the 2 rows are get swapped, right? So that's how you swap two rows in Python. You can multiply one row by another row, right? Or you can add a constant multiple of one row to another row. So what I do is I want to make some changes on the first row. That means row 0 in Python. So what I do is, so I want to obtain a new row, right? So the first row in by our counting, but the 0 index row in Python. So the chain is that I'm going to multiply, let's say 3 by the first row in Python, right? Which is I want to borrow this particular row and then add with this row to create a new first row. Right, so to do that, let's see the difference. I'm going to print a B one more time. Now, as you can see that there are some changes in the first row, right? So I make the changes from the previous output to the next output by adding the constant multiple of the second row by 3, right? So I borrow the second row, so there's no change in the second row. There's only some changes in the first row. Okay, now with this enough information, I'm gonna perform the Gauss-Jordan eliminations process to obtain the solutions of one of the example in lecture 2. So in lecture 2, you have the system. This is the example 4 in lecture 2. So the example is we want to use Gauss-Jordan elimination method to solve for the system of the form 2x1 minus 3x2 equal to 6. Right, so let me use command here. So 2x1 minus 3x2 equal to 6. And the second equation is 3x1 plus 4x2 equal to 1/2. Okay, I'm going to form the augmented matrix. The augmented matrix of the system. So the matrix consists of the coefficient matrix and the constant matrix, right? So I'm gonna call this particular matrix capital C. I need an array, open parentheses, close parentheses. So the entries, if you go back to the node, you can see that the entry is going to be 2, -3, 6 for the first row, and 3, 4, 1/2 for the second row. So this is the first row, 2, -3, and 6. And for the second row, you have 3, 4, and 1/2. And you cannot actually use the big vertical line in Python to separate the coefficient matrix and the constant matrix. Just we're gonna blend everything together in just one row. Okay, for this particular array, I forgot to have the open and close bracket. Okay, so I'm gonna print out the matrix. Okay, so this is the matrix that we have. This is the augmented matrix, for example, for in lecture 2. Okay, so to perform the Gauss-Jordan eliminations method, you can see the first row elementary row operation is to multiply the first row by 1/2. So I'm gonna change in the first row or the 0 index row. Right? So C0 is equal to 1/2 multiplied with C0, and I'm gonna have the new matrix C. As you can see, let's get changed. The first row get changed. Okay. Now, based on our calculation in the example, we want number 3 to become 0. So we need 0 here. So that means you want to make change in the second row or C1, the first index row in Python. What we did is you multiply 3 or -3 by row 1 or C0 and add it with C1 to create a new C1. Okay. And you print out C again, and this is what you got, right? So compare with the entry in the node. This is 17/2. This is -17/2. So next, you want to multiply, you want to turn this 8.5 into a 1 because you need the leading one. What we did in the node is, so C1 multiply with +2/17 by C1 to create a new C1, and you print out, you get, right, so 8.5 turn into 1, -8.5 turn into -1. Now you have the leading one in the second row. You want to, that means the entry above that has to be equal to 0. So this is -1.5. So you turn, and you want to get a new row 1. So what you did is you multiply 3/2 or +1.5 by C1, added with C0 to create a new C0. And you make the print here. And this is the augmented matrix in the reduced row echelon form that we obtain in the solutions in the lecture notes, right? So that means the solution of this particular system is x1 equal to 1.5 or 3/2 and x2 equal to -1. Okay. So hopefully you get some idea how to perform this Gauss-Jordan elimination method to obtain the solutions of linear system of linear equations. Now this is just the very small matrix. Right? Small means that you just have two rows and 3 columns, which is very simple for us to work everything out by hand like this. But if you have a more complicated matrices, then it's become very difficult task to keep track of. Lucky for us, in Python, there are some built-in functions that you can actually use to perform the to perform Gauss-Jordan elimination method to obtain reduced row echelon form. And to see that, there's another library that you need to import in. So from, right, in addition to the library NumPy that we import at the beginning of the code right here, there's another library that you can import in, which is SimplePy, right? From SimpyImport star. Okay, so that allows you to have a symbolic calculations of matrices. Okay, instead of us doing all the multiplications, divisions, or swap and row and whatnot, what the system do is that it's going to perform everything in the background and just give you the answer at the end, which is a lot easier, a lot faster for us to deal with. Okay, so now we're going to go back to this particular matrix, right? So example 4 in lecture 2. Now I'm going to call the matrix a different name. So matrix D, create an array, open parenthesis, open bracket, close bracket. Now the first row is going to be again 2, -3, 6. The second row is going to be 3, 4, and 1/2. Okay. So I want to print out D. Okay. And you can see that again, we obtained the augmented matrix of the system. Okay. Now to actually get the reduced row echelon form of this augmented matrix, what you do is you type matrix, the whole word matrix, and then of open and close parenthesis, so matrix of D. I want to perform this particular matrix and get the reduced row echelon form, so RREF. There is some code running behind it. We don't need to know how it works at this point. You just that this is the tool that we can use. So reduce row echelon form, just open and close parentheses. And if you hit Shift Enter, it will give you a few things, right? So it's gonna give you a lot of unnecessary stuff, right? So it's the matrix here, and 0, 1, right? But you don't need the 0, 1, right? You don't need the matrix, you just need the information right here that's give you the reduced row echelon form, very similar to what we obtain over here. Okay, so x1 equal to 1.5 or 3/2, and x2 is equal to -1. That's the solutions of the system, right? That's what we care about. And to just get this part of the matrix or of the output, what you do is you choose, right? Remember, I'm talking about index when starting at 0. So I just want to have the index 0 of this part of the calculations of the output, right? And not the first index the second index of the output. So I'm going to do 0, right? Just the first index of the output. And this give me the reduced row echelon form. So which is a lot faster. We don't have to do a lot, do the calculations by hand, even though doing this by hand give you a lot of insight into how to perform certain tasks in Gauss-Jordan eliminations method. Now, with this particular task, with this particular knowledge, we're gonna move on to example 5, right? The task is to create a new matrix or augmented matrix and perform reduced row echelon form using this particular command. All right, so for example 5 in lecture 2, I got, so the augmented matrix, I call that the matrix E. I need to create an array, open parenthesis, close parenthesis, open bracket, close bracket. And the first row include 2, -1, 4. The second row is -6, 3, -12. Okay, now, so let's print out E, make sure that this is working. So this is working. So I'm gonna perform the reduced row echelon form. Matrix E, doing reduced row echelon form, and I just need the first output entry of the output. And this give me this particular augmented matrix in reduced row echelon form. Now, if you go back to example 5, you will see that match with the answer that we got. Right, so as you can see, this is infinitely many solutions. Okay. And let's move on to even though it's give you the answer, it's not actually give you the solution set of infinitely many solutions. Right, so you have to go back and choose either x1 or x2 to be a free variable to write down the solution set of the infinitely many solutions case. Now for example 6, you have another system. Now let's create the array of the matrix for that particular system. Right? So the first entry of the system in example 6 is so 2, 6, -3. That's the first row. The second row is, I keep forgetting, closing, open and close brackets here. So the second row is 1, 3, and 2. All right, so let's print out this particular matrix to see if that works. So it works. Now perform the reduced row echelon form on the matrix F, and just going to choose the first entry of the output. And this is the augmented matrix that we get. So it's a little bit different from what we have earlier in the note, but overall, right, so there's some okay, so what they did, we can actually divide both sides for -7, which is a little bit different from what we have in the note, right? But overall, the output gives you the idea that this is the inconsistent system. So therefore, because 0 cannot be equal to 1, so therefore there's no solutions in this particular case. Okay, now we have one more example in the note, which is example 7 for the homogeneous system. Okay, we also is going to create a matrix. So the first row include the entry of 1, -1, 3, 0. And the second row is 2, 1, 3, 0. So again, this is the example 7 in our notes. So let's print out G, and that's working. So perform the reduce row echelon form on G and just choose the first entry of the output. And this is the answer, right? With match with our calculations. And of course, you have to go back and write out the system because it's the augmented of another equivalent system. And this indicate that you have infinitely manageable solutions based on the one theorem that we have that because the number of equations less than the number of variables, so the system has infinitely many solutions. And you go back and write down the system again to choose that x3 is the free variable to write down the solution set. Okay, so hopefully at this point it gives you some idea of how to actually perform or to obtain the solutions of the augmented matrix using Gauss-Jordan elimination method. You can either do everything by hand, or there is a command that you can use to obtain that augmented matrix in the reduced row echelon form. So let me stop right here, and in the next video, I'm going to show you the new lecture, which is lecture 3, applications of the system of linear equations. Thank you.